Okay, so since we kind of went over the class in lab there to begin with, we will start lecturing here on our first chapter, which is chapter 12, and it's about equilibrium. And essentially, this is really pretty much the main topic of this class. Like I said earlier, we're going to talk about every type of equilibrium that you, again, probably didn't want to know about. We will cover in this particular class. Now, when we talk about equilibrium, and sort of the equilibrium condition, it does involve a certain type of reaction that is taking place. And that type of reaction are ones like this, which you might have seen previously in 200A there. It is these reactions that have these arrows that are heading in both directions. These are reversible reactions. You probably maybe talked about these type of reactions when you talked about electrolytes. Weak electrolytes are these guys that have these arrows that head in both directions. And because this reaction heads in both directions, these are referred to as a reversible reaction. And it has really two directions, right? Our guys on the left-hand side of the arrow are reactants, right? And our products, right, are on the right-hand side of the arrow. And as the reaction heads from reactants to products and heads in this direction, this is what is sometimes referred to as the forward direction of this reaction. And what makes these type of reactions kind of interesting is at some point you will create enough products that those products will actually decide we would like to also react with each other. And it will actually send the reaction heading in the opposite direction. So at some point you'll build enough products that the products will actually start reacting and forming some reactants in that situation. And this is what is referred to as the reverse direction. Now, when people think about sort of chemical equilibrium and equilibrium being reached, they usually have a incorrect sort of understanding of what the word equilibrium means. They hear the word equal and they think equal amounts on both sides of the arrow, and that is actually not the case. So when something reaches equilibrium or chemical equilibrium, it doesn't necessarily mean that you have the exact same amount of reactants and products. What it is actually referring to is kinetics. And if maybe you did kinetics, in my experience, that's like the last day or so, 200 days, just throw it at you really quickly at the end of the semester. But kinetics deals with the rate of reactions. And when something reaches chemical equilibrium, as we'll talk about a number of times here in this chapter, what that essentially means is the rate of that forward reaction will actually equal the rate of the reverse reaction. So they're actually occurring at the same rate. And what that will essentially do is lock everybody into place in terms of their concentrations. If you're dealing with concentrations, our pressures, for example, if you're dealing with some gases, it will basically be able to maintain their concentrations or their pressures, and they will continuously be able to maintain that, and they really won't change over the period of time unless you do something to screw it up. And if you don't do anything to screw it up, it will just keep going back and forth. And that happens because if you think about it, just as quick as you go this way, they're just going to come back the same way and the opposite direction just as quick. And that just keeps everybody exactly where they're at when they reach equilibrium. And again, it doesn't necessarily mean that you have the same amount on each side of the arrow. And when we think about a reaction that has reached chemical equilibrium, sometimes when we look at a reaction that has reached equilibrium, to us, sort of on the macroscopic sort of idea or the big scale, it may look like it's over. So, for example, if we had a beaker and we added some reagents to this beaker, and this beaker turned reddish in color, and this beaker will stay red, and it may look to us like nothing's happening, the reaction's over, it's obviously staying red, it's not changing or anything like that. And on sort of the big level, there's really not much changing sort of visually to you. And if this was that same reaction where A and B went to C plus D, if you were to sort of super zoom in, what you would actually see is there's actually a lot of activity to maintain, for example, that red color that you just visually see. There's a lot of A's going to C and D's, and C and D's going back to B and A. So there's a lot of activity happening sort of below the surface, if you will, to maintain, for example, that red color. So sometimes when people look at an equilibrium reaction and they put it in there, it just looks at them like nothing much is happening. It's kind of over. I saw the red color develop and it's done. But there is actually a lot of activity that's necessary to, for example, just maintain that red color that you are visually seeing on sort of the big scale. So equilibrium is really not static. There is a lot of activity happening and you may not be able to see it, but it again is a lot of that forward direction happening and that reverse direction happening. So equilibrium, like I said, is sort of static on the macroscopic level, but on the microscopic level, there's a lot of activity happening. So what do I mean by that? So for example, again, let's say initially we had in this reaction like 4 molar of A and like 2 molar of B and like nothing of C and D. As this reaction would occur, for example, in this situation, the only option for this reaction to happen at this initial situation is which direction does this reaction has to proceed, in the forward direction or reverse direction? It would only have one option in this case. You only have reactants, which means at the beginning of this reaction, all you would have happening now is the forward direction, right? Because you have no products available to you to even make reactants and do the reverse direction, right? So it's all going to be in the forward direction. So as time goes on, we're going to lose some of our reactants, right? And we should make some of our products. At some point, you will build up some products, which will then kick off the reverse reaction basically occurring. And eventually you will reach that chemical equilibrium. And again, at that point, maybe you got 2 molar of this guy, 1 molar of this guy, 3 molar of this guy, maybe 2 molar of this guy. And at that point, once it reaches that equilibrium, every one of those reactants and products, again, will be able to maintain their concentration where they're at as long as you don't do anything to screw it up. And again, that is what we're talking about. As you can see here, my just made up example of those numbers, they don't equal the same amount on both sides, but they will be able to maintain those concentrations again as long as nothing messes up the equilibrium. One of the nice things about these type of reactions, thank you. One of the nice things about these reactions are these reversible reactions is, even as we'll talk about later on in this chapter, if you screwed up this reaction and did something to mess up the equilibrium, it will want to self-correct itself and it will self-correct itself back to an equilibrium condition. So that is sort of the goal of these type of reactions, is to always get back to an equilibrium sort of condition. So even if you did something to screw it up, it will really self-adjust itself and get itself back to that equilibrium where the rate of the forward reaction and the reverse reaction will equal each other. So if we look at a reaction here like the formation of ammonia, a little N2 plus a little H2, a little NH3. We'll balance it like we're in chemistry class here, maybe. There we go. And again, initially here in this reaction, based on the graph that we see, we're basically starting with only reactants. So we can see we have a good concentration of H2. We have a good concentration of N2, which is our reactants. And here initially to start out with, we really have no products. Now, in order for this situation to occur, as we just mentioned, because we only have reactants at this point, there's really only one option for the initial sort of direction of this reaction. It will go to start to make some products. The result of that is, as you would expect, if you start to make products, the only way to do that is to use reactants. So we would expect our reactant concentration to start to decline over time. So we will expect to see it come down. At the same time, we would expect to see our product concentration start to increase with time. And as you can also see on this graph, at some point, we kind of see almost a leveling out of our reactants, right? Because we're now starting to see a pretty good increase of our products, which means at some point, again, we're going to kick off that reverse reaction that's going to take place. And that's going to minimize how much reactants are going to go to products, because now we're going to go back the other way. But eventually what we'll see in all three of these cases, our products, our reactants, is at some point in time, they will all basically flatten out in terms of their concentration. Yeah. So they'll all basically plateau out and flatten out. That means that when you hit a straight line, is the concentration changing? Concentration is not changing on this graph, right? Concentration is the y. So if you're running a straight line, your concentration is staying basically the same, right? It's staying consistent and constant here. And it's at that point where you see everybody's concentration in this case level out and just stop changing, is the point where chemical equilibrium has been reached. And that is the point where we see the rate of that forward direction will equal the rate of the reverse direction. There's really, as you can see in this graph here to the right of that dashed line, there really is no change in concentration of anybody. And that's, again, as quick as you lose some reactants to products, they're coming back the other way and making our products back to reactants. So again, a kind of a no net change is happening in the concentrations of everybody. And that is where we get our chemical equilibrium being reached. Now, if we look at this reaction here, as I mentioned, we could see initially we have no products. So the forward direction is going to occur as we start making enough products. These guys are going to come in contact with each other, start colliding, and start heading back the other way again until we reach chemical equilibrium at this point. So graphically, if you ever look at sort of a graph representing equilibrium or when equilibrium is reached, you're looking for that point where the forward direction and that reverse direction equal each other. And as we saw in the previous graph, that is really the point where you'll see all your reactant concentrations, all your product concentrations basically level out, and you won't see any more changes occurring. And that is where you know that is the point where chemical equilibrium basically has been reached. Any questions on that there? So let's take a look at this guy again here. This H2O plus the CO goes to H2 and CO2. So let's say we had a system at equilibrium and we let this guy go to equilibrium in a container and reach equilibrium. And at this point, maybe we got a little bit of reactants and products happening. So in this particular case, let's say we decided to add some more H2O to this container. What is going to happen to the concentrations of everybody when we do that? So take a moment here for everybody here. If we added more water to the system, what's going to happen to their concentrations? That is concentration, as you may be familiar with, hopefully. And when we talk about concentration, by the way, we typically are talking about molarity, right? Which is moles per liter. Yeah, so that is typically the unit of concentration we're talking about here. So for each of these, decide what's going to happen. Will they increase? Will they decrease? Will there be no change that will occur? So take a moment, think about if you added more water, what would you expect to happen in this case? Okay, so let's take a look and see. So in this particular case, if I added more water, water is a reactant, right? Which is on our left-hand side of the arrow. These again are our products. So if I add more water, which is over here, will that kick off the forward direction or the reverse direction? Which direction do you think? Should kick off the forward direction, right? One of the things that affect how things react, right, is just the availability of reactants or products, right? So if you have more of, say, reactants versus products, those guys are going to find each other, right, and start colliding and start the reaction to take place. So basically in this case, because we added more reactants, we would expect our forward direction basically to kick off because, again, just from availability, we're going to have a lot more availability of these guys being able to find each other easier and quicker. And that's going to cause the forward direction basically to occur in this case. That would mean that the concentration of CO in this case, should it go up, down, or stay the same? It should go, I think I see somebody pointing down. That would be right. You're halfway there. You're almost committed. Like, I'm going to go down and maybe half. kind of happen to change at the last minute and go up. But you are pointing down, so that is correct. And again, the idea there, right, is we need water and CO to come together, right, to react, to make our products. So we should expect, because the forward reaction is occurring, the reactant concentration should be decreasing at this point, because again, that's the only way we can make our products. With that being said, we should expect now the formation of our products here, and we should expect these guys' concentrations to go up for both of those again, because at this point we're kind of forcing the forward direction of this reaction to occur, and that's going to make our products occur. How about water? What's going to happen with water? It will overall go which direction? It's actually going to overall go down, right? But because you're adding it, what we're going to see with water is it effectively will go up because you added it, right? So it's going to skyrocket, right, in terms of its concentration. But as soon as it starts reacting with the CO, we then should start to see it come back down, right, as it's reacting. It may actually end up higher than what it started with, and that's only because you added it, right? So you put artificially in there a lot more than was there to begin with. But the overall trend we should see with our water is it should, as it starts reacting in that forward direction, is to start to come back down after obviously we added to it. Any questions on that there? All right, same reaction here, but in this case, we're going to add some H2. So what's going to happen to everybody's concentration in this case? So take a moment there and think about, will they increase, decrease, stay the same? All right, so in this case, we are actually adding H2, which is over here on our product side. So forward direction and reverse direction, which direction should happen in this case? Yeah, it should be the reverse direction. Again, for the same reason, by adding more H2, we now have a lot of products that can find each other a lot quicker and easier. And that definitely is going to kick off the reverse direction in this case. And that should mean in the case of CO2, it should go down, right? Again, we need in this case, because the reverse direction is occurring, we need both of our products to come together, right, to send that reaction back in the reverse direction. That would then mean that we should be actually making more reactants in this case. And because of that, we would see the concentration of our reactants increase in this case. And in the case of H2, much like we saw with water, we will actually see overall it should come down. But once again, it's going to artificially go up because you added it. But once it starts reacting again here with our CO2, we should start to see the concentration again come back down in that case. Any questions on that there? So let's talk a little about the equilibrium constant and the application of the equilibrium constant. So if we have an equilibrium reaction like this, we could actually write what is referred to as the equilibrium constant. And the equilibrium constant is abbreviated with a capital K, and that is the equilibrium constant. And I say capital K because if you talked about kinetics in 200A, you maybe saw little k, which is the rate constant. And they are two different things, even though they are kind of related to each other. But here in this class, we really focus in on capital K, which is the equilibrium constant. In fact, this class is brought to you by the letter K. We will see it in every chapter pretty much, and it is every type of K you, again, may not even want to know about. So what is the equilibrium constant? We can have a relationship of the equilibrium constant is essentially the concentration of your products divided by the concentration of your reactants. So it is the proportion of your products to your reactants, the concentration. We actually do take into account the balanced equation and the coefficients. So as you can see here, this is our product and the coefficient is a 2. It would be the concentration of NO2 and we would square it because of the coefficient. So we do have to take into account the coefficient there divided by the concentration of our reactants. And as you hopefully know, right, if there is nothing written there, it's assumed to be a 1. We typically don't write 1 in chemistry a lot on things. And that is essentially, this is essentially to the power of 1 in this case. So we take the ratio of our products divided by our reactants. and it gives us this value here, which is known as the equilibrium constant. In general, you could take your products divided by your reactants, again, to the coefficients, and this will give you your equilibrium constant value. This is also sometimes referred to as a Kc value. And a Kc value, I'm going to go with concentration for C. So since we use concentrations here to calculate it, this is what is sometimes referred to as a Kc, also known as the first of our 22 K values that we will talk about in the semester. So Kc typically calculate with the concentrations. Now, one of the things about the K value that's a little bit different is there typically is no units associated with it. So most thing in chemistry, we want units, but with K values, we actually don't use units. It is actually just a number. And it is a number that tells us something about the reaction. So for example, if I had a large value of K, the equilibrium constant, when I reach equilibrium, would you think I would mainly have reactants or products present? If I had a large value of K. I should mainly have products, just math speaking, right? If I take a large number on top divided by a small number, I get a large number, right? Which means I need to have more products than reactants. And I would mainly perhaps have products at equilibrium. And if I had a small value of K, it will basically tell us kind of the similar thing. And the only way to get a small value of K is you would need a smaller number on top divided by a larger number on the bottom. And that would mean that I mainly have reactants when I reach equilibrium. What is considered a large value or a small value? Well, it is obviously the large number of 1. Yeah, 1 is considered a large value for the equilibrium constant. Anything that is 1 and above is considered large. Anything that is less than 1 is considered a small value. As we will see as we go through the different chapters and talk about equilibrium, there is a wide range of large and small. You can have an equilibrium constant that has a value of times 10 to the 54, which is extremely large. You could also have a K value that has a value of like times 10 to the minus 34, which is extremely small. And you can have K values anywhere in between there. So we could have really large ones, which regardless if you have a large value of K or a small value of K, it still is a reversible reaction. So what I mean by that is if we did have a reaction that had a large value of K, like times 10 to the 34, even though essentially we're going to only have product because it's super large, it's going to mostly go in this direction. If I had a times 10 to the 34, there is always going to still be a smidge of it heading back in the other direction because these are still reversible reactions. So even at the extremes where we have really large values of K or really small values of K, even though it is really favored to go kind of in one direction, almost a one-way street type of reaction, it will still go in both directions and still occur and reach equilibrium. And that's different than a non-reversible reaction, right? A non-reversible reaction, right? We see one arrow, right? Which means it's not coming back. It's just dumping off to the product side and it's not really coming in the backwards direction. That is also why we only have equilibrium constants for reversible reactions, right? So if it goes in one way, there is no reactants coming back. So there is no products over reactants. It's just a one-way street. So all these reactions are like a two-way street where it's always going back and forth. In some cases, it may be going back and forth, relatively equally. And in some cases, it's mainly going in one direction, just a little bit back in the other direction. Any questions on that there? The value of K, which is known as the equilibrium constant, is a constant value regardless of what you do. The only thing that can affect the actual value of the equilibrium constant is temperature. So temperature is the only thing that can have an actual effect on the value of the equilibrium constant. Now, What I mean by that, for example, is if you did an experiment, and this is something that sometimes people struggle with sort of wrapping their head around it. So let's just say we were doing this reaction here, and let's just say we did it at a temperature of like 25 degrees Celsius, right? And let's say we did multiple experiments of this reaction and we let it get to equilibrium. Let's say experiment one, we started with 5 molar of this guy, 3 molar of this guy, nothing of these guys. Let's say experiment two, we started with nothing of these guys and maybe 2 molar of this guy, 3 molar of this guy. Let's say experiment three, we had a little bit of this guy, a little bit of everybody sort of involved in here. Every single one of those reactions, if we did it at 25 degrees, should they have the same equilibrium constant or different? It should end up being the same, yeah? So even though you started with all reactants in this case, you started with all products in this case, you had a little bit of everybody in this case, right? They all should have the same K value as long as that temperature stays at 25 degrees for each of those experiments. So you may be thinking, well, if I started with, say, more in one and less in the other, how could I end up with the same value of K? So a really simple sort of example of that is just think about this idea of, let's just say I wanted my equilibrium constant value to be 2. So let's say I did a reaction and I want my equilibrium constant value to end up as 2. There are many different ways that you could get to 2, right? I could get to 2 by taking 2 divided by 1. I could get to 2 by taking 4 divided by 2. I could get to 2 by taking 8 divided by 4. They all equal 2, I hope. Yeah, I'm going to stop there before I screw up, but they all equal 2 in this case, right? They're all different numbers, right? But the ratio of the product, the top guy to the bottom guy in each of these cases is the same ratio. And that's the idea behind the equilibrium constant, even though you may start with more in one experiment or less in the next. When they come to rest at equilibrium, as long as the temperature doesn't change, they will come to rest at the same proportion of products to reactants that will give you the same value for the equilibrium constant. Any questions on that? Yeah. It, the are you talking about this part here? Yeah, that it comes directly from the coefficient from the balance equation. Yeah. So you definitely have to include those in there, otherwise you will not get the correct equilibrium constant. Yeah. And that's why always, not a super issue and a lot of times in this class, but if you are given an equation, you should always make sure it's balanced like normal. And it's definitely important in terms of when you go to do the equilibrium expression. Also really important here, as I mentioned earlier, there was a lot of problems where you'll have to come up with the equation, right? So not only do you have to come up with the equation, you got to also make sure it's balanced, right? So you always want to make sure you do that. Otherwise, you'll have the wrong one. Now, for example, let's say I did the exact same 3 experiments here, right? I did the exact same 3 experiments, but I changed the temperature to 40 degrees Celsius. For all 3 of those experiments at 40 degrees Celsius, will the equilibrium constant be the same or different? So if I redid all 3 of these experiments, I kept the temperature at 40 degrees for each experiment, should the equilibrium constant be the same or different for each of those experiments? Should be the same. Again, we kept the temperature 40 degrees, right? For each of those experiments should give us the same equilibrium constant. When I compare the equilibrium constant at 25 degrees to 40 degrees, are they the same or different? They're going to be different. So that is what we're talking about when we talk about the temperature change is what affects us. So when comparing the K value for this reaction at 25 degrees to 40 degrees, we would expect a different K value. But as long as we keep the temperature the same for each individual experiment, they should be the same value. But in comparison between 2 different temperatures, you will get 2 different K values. Any questions on that there? Okay. So as I mentioned before, if you look at the K value, it is a really important value because it does give you an indication as to what is going on in that reaction. Do you have reactants that are equilibrium? Do you have products? It's also really important, as we'll see as we go through different chapters, in terms of calculations. Now, depending on the type of K value that you have, is it large or small, it may or may not allow you to do certain types of calculations when you go do the problem. There are certain K values, as we'll talk about, that prohibits you from shortcutting a calculation. Yeah. And there are some K values that allow you in some cases to kind of shortcut a calculation and take a little quicker route to the answer. And so it's always important to look at those. The K value that you see written is also, as I mentioned, specific for the temperature, and it's also specific for the way the reaction is actually written. So what are the reactants? What are the products? The way it's written, and the K value that goes with it is specific for that. So if we had a K value here of 10 for this one, it is specific for these guys being our reactants and these guys being our products at a specific temperature. We'll talk about a little bit later on this chapter. If you switch that reaction around, it does affect the K value, and we'll talk about how it affects it just a bit. So here, if we take this reaction here, we got Mickey Mouse, we got a couple of these guys, and we make Mickey after a long day upside down. And the K value here is 25. When this reaches equilibrium, should I mainly have reactants or products in this case? We should have products, right? This is considered a large value of K. It's over 1. So again, anything over 1 is considered a large value. We should mainly have products in this case. And it means mainly the forward direction is occurring. Still, we're going to have the reverse direction occurring. But this is considered a large value of K. So in a homogeneous equilibrium, and homogeneous, as you may be familiar with, it's the same meaning of like homogeneous mixture. In a homogeneous mixture, right, everything looks the same throughout. In a homogeneous equilibrium, it means everybody's in the same phase. So in this particular case, everybody's in the gas phase. And we could write an equilibrium constant here for our concentrations, taking our products over our reactants. And again, we're going to square them because of the coefficient, obviously to 1 because of the coefficient. But in this particular case, since they are gases, when we think about gases, right, we think about a property known as pressure, right, when we associate with gases rather than, dare I say, concentration. Throws back to our classic, a little PV equals nRT action. Yeah, I know it's not 200A, but we might see this guy. That is the ideal gas law. That is the pressure in atmospheres, right? That is the volume in liters. That is moles. That is your gas constant, 0.08206 liters atmosphere Kelvin mole, or 0.0821 people like to round these days. And that is your temperature in Kelvin, right? All right, Kelvin, in this particular case. So we sometimes do deal with pressures when we're dealing with equilibrium. And we can write an equilibrium expression that deals with pressures rather than concentrations. And it works the same way. This means we take our products, so that is the partial pressure of our NO2, and once again, we're going to square it because of the coefficient, divided by the partial pressure here of N2O4, which once again has a 1 as a coefficient, so we're not going to really do much with it. And unlike a Kc value, this is what is sometimes referred to as a Kp value. I'm going to go with pressure for the P there because it kind of makes sense, I suppose. And now within 5 minutes, we now have 2 K values in our ever-growing list here. So the Kc value is still products over reactants, dealing with concentrations. The Kp value is still products over reactants, but dealing with pressures. When we talk about pressure, by the way, and you're dealing with equilibrium problems, and later on in this chapter, when you're dealing with calculations that involve equilibrium, the standard unit of pressure is your atmosphere. Yeah. So your atmosphere is your standard unit of pressure. 1 atmosphere, right, is 760 torr, 760 millimeters of mercury, right? So if later on in this chapter you come across a problem that does involve pressures and you need to do an actual calculation with them, you need to actually convert your pressures into atmospheres before you kind of do the equilibrium calculation. And even in a problem where sometimes people kind of mess up the problem is sometimes they may be given pressures in like millimeters of mercury or torr, and they're asked for the answer in millimeters of mercury or torr. So they figure, oh, I'm good. I could just leave it in that and do the calculation. You do have to kind of put it into atmospheres, do the equilibrium calculation first, and then afterwards convert it back. So kind of like when you use the ideal gas law, right? You could be given pressure in many units, but you got to pop it into atmospheres before you go in there, and then you can convert it afterwards. So same deal with equilibrium. Pretty much these are the units, and most real equilibrium calculation we'll do a little bit later on this chapter. You should always be using molarity in most cases for concentration or solutions, and atmospheres for pressures. These are really the 2 units, that you should definitely be using if you're doing some true equilibrium calculations. By the way, I didn't mention it, but obviously, if you had values given to you and you wanted the value of the equilibrium constant, these values that you would put in here, they do have to be equilibrium concentrations or equilibrium pressures. You cannot put in their initial like concentrations or pressures. It has to be what they are at equilibrium. So obviously, they have to be the equilibrium values to put it in there. In most cases, the Kc value and the Kp value do not equal the same value. Sometimes they do, but in most cases, they're not numerically the same value, but they do tell you the same thing. So if you have a large value for Kc, you probably should also have a large value for Kp. Maybe not as large, but something still considered large. And if you have a small value for Kc, you should also have a smaller value for Kp. If you think about the guy on the right, it is based on atmospheres, which is pressure, which means if you have a large value of Kc, that means you have a lot of products, right? And if your products are gases, they probably have a majority of the pressure in that situation, right? And that will give you a larger value on top for your Kp, and that will give you a larger value for your Kp. So they should sort of agree with each other. Now, in certain situations, you may be given enough information, for example, to calculate one versus the other. So maybe you're given all concentrations, but you really want the Kp value, or vice versa. You're given all pressures, and maybe you want the Kc value. So there is a way to go between the two, and it is here in the box. The Kp value equals the Kc value times R times T delta N. This R is the gas constant that you use in the ideal gas law, so 0.08206, or if you learned 0.0821, which maybe that's what you learned. The temperature here does need to be in Kelvin, yeah, so that again does need to be in Kelvin. The delta N here, that is the change in the number of moles of the gases. So we're just counting gases here for delta N. And you should do products minus reactants. So you should do the moles of the gases on the product side minus the reactants. By the way, don't overcomplicate it. It is just a coefficient. That is a 2 moles of gas on the right, and that is 1 mole of gas on the left in this particular example. So you look at everybody that has G's, and to do that. By the way, you cannot write a Kp value if you don't have gases, right? You don't have gases, you don't have pressure, so you could really only have a Kp value if you got some gases involved in the equilibrium. If you don't have them, then you can't really write a Kp value. So if we looked at something, say like QA goes to B in this case, what is delta N in this case? How many gas molecules are there on the product side? 1. There you go. Yes. And on the reactant side, there are 2, right? 1 minus 2 here is -1. Yeah. That negative is quite important mathematically speaking when you do this part of your calculation. When I take the RT to the 1 versus the RT to the -1, what is the difference mathematically? This one is just to the 1, it stays the same basically. This is 1 over RT, right? So it's the inverse of it. So sometimes people make a very common error. They just take the difference between products and reactants, forgetting about negative or positive. It does make a big difference when you do the calculation part. So don't disregard the negative here if you do get a negative, because mathematically it does mean something different. Any questions on that there? God.
That's RT.
It is RT. Right here? Yeah, it's RT. Yeah. It's that part of this equation, obviously. And obviously there's the KC in front of it equals the KP. All right. Now, in a homogeneous type of equilibrium, we can write our equilibrium expression like normal and take our products over our reactants. So we take our KC here, which is our acetate divided by our hydronium ion divided by our acetic acid and our water. Now, when we write the equilibrium expression for a reaction, it is always products over reactants. But there are certain things that basically do not affect equilibrium or really do not change. Water is one of those things. Things that are a pure liquid, their concentration is so large usually that it doesn't change as the reaction is taking place. They're relatively constant. So things that have an L do not get included when you write the equilibrium expression. So if we were to write the equilibrium expression for this reaction, scratch that out, right here is actually the proper equilibrium expression for that. It is our products over our reactants. We do not include pure liquids in there. I'll jump a couple of slides here, but essentially we do not include in the equilibrium expression anything that is a pure liquid or anything that is a solid. A solid for the same reason, just sitting there. Yeah, it's not doing much. So a solid will not affect equilibrium. It's just kind of hanging out there. It's not really active or anything like that. So if you have anything in the equation that's a liquid or a solid, you do not put it into your equilibrium expression. That means what we do include is what's left over, which basically is anything that is aqueous, which means a water environment. As you hopefully know, aqueous is a solution, right? There is a difference between aqueous and L, which is liquid. What is the difference between those two? What is the difference between an L and something that's aqueous? L is a pure substance, like water by itself. Yeah. Something that's just a pure substance. AQ is aqueous, which means you took something and dissolved it and made a mixture or a homogeneous mixture. So if you took water plus some sodium chloride, that comes together and makes a sodium chloride solution that's aqueous. Solvent, right? Two things mixed together to make a solution. So there is a difference, even though they're both in the liquid state, right? They are different things. And the other thing that's included are things with gases. So when we write equilibrium expressions, Kc, Kp, it doesn't matter, whatever equilibrium expression it is, those are the two things that should always be included. And the two things that should not be included is things that are liquids or solids. In a lot of cases of reactions that we come across, water is a very common thing we leave out. What happens if my water was in the gas phase? Should I include it or leave it out? What do you think? 50-50 shot. Can only be wrong twice. You guessed two really bad things, I suppose. Yeah. Should I include water that's in the gas phase? I should. It's in the gas phase, yeah. So it's steam, it's moving around, right? It's got some activity happening, so it is plays part in it. So, but water in the liquid phase does not get included. So liquid and solid does not get included. Gases, aqueous things do get included. As we talked about earlier, again, it is just a number. There's no real units that go with it. And the truthful reason for that is they don't usually cancel out nice and pretty, usually when you do an equilibrium constant. So we just kind of leave the units off. All right, so take a moment for each of these, write the Kc expression and also the Kp expression. so let's take a look. So again, regardless, again, what the little subscript is, KC, KP, as we'll see, KW, KA, KB, all these things. They're all always the same. They're all the same thing in a sense. They're all equilibrium expressions. It's always products over reactants. So in this particular case here, if we're writing for our first one, our KC, we would take the concentration of the NO2, and again, we would need to take it to the fourth power because of the coefficient here in our balance equation. That would be multiplied by the concentration of our O2. Once again, it is basically to the first power there. That is our products, again, divided by our reactants, which is the concentration of N2O5. And once again, because of the coefficient here, we will need to take it and square it. Any questions on that one there? Can I write a KP for this one? I can. There's definitely gases all over the place. We would write our KP the exact same way, except instead of using concentration, we would do the partial pressure of our products, which is NO2. We still need to take it to the fourth power because of the coefficient. That would be times the partial pressure of O2 to the first power divided by the partial pressure of N2O5. And again, also like we did on the previous one there, square it because of the coefficient. On the bottom one here, we could write our KC in this case, and it would be our products, which would be the concentration of H3O plus. Again, it is to the first power, times the concentration of F minus, also to the first power, divided by the concentration of HF, also to the first power. Do I include the water in this case? I do not, because again, it is a pure liquid, so we would not include it. Can I write a KP for the bottom one? I cannot. There is no gases, right? So there's no KP value. Any questions on any of those there? Now, what happens if I had, say, something like how's that? Something like this. What would the KC value be? It would be concentration of B, and we would square it. And because this is a solid and there's nothing else there, there would be no reactants, right? So basically that would be it. Now let's just say, for example, you had something like, you know, in this case, if I were to write the K value for this, I would not include the products, right? Because it's a solid. So what should I do? I should do 1 over the reactants, yeah, A and B. Yeah. So if you happen to have something on the product side that's not included, you just do 1 over the reactants in that case. If you have something on the reactant side that's not included, and that's the only thing there, then you basically it's just the products. Any questions on any of that there? So again, if you're asked to write the equilibrium expression, that is what we're looking for right on the top there, one of those two guys. All right, so let's take a look at a calculation here, perhaps. We have some equilibrium concentrations for the reaction between carbon monoxide and chlorine. The concentration is 0.012 for CO, 0.054 for Cl2, and 0.14. What is the Kc and Kp value here? So take a few moments there, and the Kp value. It would make sense to go after which one first in this case? Which K? The Kc, since we're given concentrations, right? So since we're given the equilibrium concentrations, all we have to do is write the expression and basically plug it in there. So that would make the most sense. Our Kc expression in this case would be our products, which is concentration of CoCl2 divided by CO and our Cl2 in this case. Here we will just put in our numbers. And again, these are the equilibrium concentration, which allows us just to go right into the expression. So we got 0.14 divided by 0.012 and 0.054. So again, if we do this 0.14 divided by 0.012, I would recommend hitting equals, divided by 0.054. And you will get 216 in this case. Now, reminder that sometimes people really screw it up when they go and punch it into their calculator. They try to punch too much stuff in at once. Always a good idea to use the equal sign more than not. So again, I would take this top number divided by the bottom first one, hit equals, divided by the next guy, and then hit equals again. You will get the right answer. If you try to put everything into your calculator at once, which is a super common error people make, and you don't do parentheses correctly, you will get the wrong answer. So just keep that in mind as you go through it. It's chemistry, some sig figs, maybe. I don't know. We'll see. 220 maybe on that if we want to sig fig it out there with two sig figs all over the place. Give or take, We'll see. Do you need to do that? Was that? You should try, I would say, since it is a chemistry class. I'm sort of a chemistry teacher, maybe. One of those things are true. I don't know which one it is. It is a chemistry class, I think. But yeah, you should always try to get the right one. I'll be honest with you, unless you're horrible at it, you probably won't lose points. Yeah. But I'm more interested probably in the calculation, but you should try to get it to the right number of sig figs. Like usual, though, as you maybe learned right in 200A and 100 as well, you shouldn't really round too much right till the end. So try not to round too much. But you should try to clean it up. If I see your answer and it's like, moving and I got to flip the page around to get the rest of the digits, that's not so good at that point. But if you miss it by one or so or something like that, probably won't be an issue unless it's pretty bad all over the place and stuff like that. So you definitely should. Now, I personally would, if I were doing this problem, I probably would continue on with, that number in my calculator and go on to the next part of it. But since in this case, we are trying to give an answer as to one of the answers we're looking for. So here I would try to at least clean up that one for the answer part of this part of the question. 220 here in this case, again, no units as it's an equilibrium constant, so we don't need units. It's just a number in this case. At this point, we really can't go directly and calculate our Kp using the pressures because we don't have the pressures. But now that we do have the Kc, we could use that equation that we saw that relates the two together. And again, that's the Kp is equal to the Kc times RT delta N. Here, we do need to convert our temperature into Kelvin, so a little 273 action, right? Nobody uses the 0.15, do they? You could use it if you like. I teach at a school where they make the students do the 0.15. So we'll go 347 Kelvin here. The R again is our constant. We want our delta N. And again, here we do want to go products minus reactants. So the moles of the products minus the moles of the reactants. So on this side, the coefficient is 1, which means we have 1 mole of gas on the right-hand side, minus our reactants, which is a 1 and a 1. So that is a 2. So it is minus 1 in this case in terms of our delta N. Our products minus our reactants. At this point, we have everything we need. So our Kp, again, depending on which number you went with, if you went with the 220 or you went with the 216, you would end up with 0.08206 or 201. If you want to use that number, is okay. 347, and again to the -1. Once again, you probably want to do that part first on your calculator. So maybe 0.08206 times 347. Take the inverse of it, either go 1 divided by your answer or take it to the -1 power. And that'll get you something like a 220 times 0.0351187. And if you times it by the 220 number, you get a 7.7. Or if you times that by the 216 sort of number there, and you didn't really round as you went on, you maybe got like a 7.6-ish type number. I'll take either one probably. You wouldn't be in trouble on either way if you did it. Yeah. First off, any questions on the calculation? Is this a large value of K or a small value? It is a large value of K, which means in each of these cases here, because it's the same reaction, we would expect mainly products at equilibrium. Again, as you can see, numerically speaking, the Kp and the Kc are not the exact same number, but they both are considered to be a large value of K. And that, again, they should agree with each other in that sense. So you shouldn't really end up ever with like a large value of Kc for the same reaction and a small value of Kp, because something probably went wrong in that case. Any questions on that calculation? Yeah.
So is it both of them that if they're greater than one, they're considered a large value?
Yeah, so any K value, regardless of what the little subscript on the bottom is, any K value that is basically larger than one or larger is considered a large value of K. And anything technically less than one, anything with a kind of like a negative exponent, or point something is considered a small value. And so even though they're not the same sort of magnitude in terms of their numbers, they both are considered large in this case. Other questions? Let's try another one here. The equilibrium constant Kp for this reaction is 158. We're actually looking for an equilibrium pressure of O2 in this case. If the equilibrium pressure of NO2 is 0.4 and NO is 0.27. So let's see what you come up with. I'm not sure if on your notes that 2 is there or not. If it isn't, you might want to add it. Okay, so let's take a look, see how you're doing. So clearly in this case, we want to think about the information given to us. I have a Kp value. I got some pressures. I'm looking for a pressure. So clearly, right, it makes sense to start with our equilibrium expression, our Kp expression that deals with all that. So our Kp in this case would be our partial pressure of NO. We again would need to square it because of the coefficient that's there. That would be times our partial pressure of O2. Coefficient is 1, so we don't really have to worry about it. Divided by our partial pressure here of NO2. Also need to square it because of coefficient. That equals 158 in this case. At this point, we do have our pressures of 2 of the 3. We are looking for this guy here. So our NO is 0.27, again squared, times the partial pressure of O2, divided by our 0.4, also needs to be squared, times 158 in this case. Remember, to move something to the opposite side of the equal sign, you do the opposite sort of math operation. So since this is being divided on the bottom, we need to multiply that to the other side, right? This guy is being divided on the top or multiplied on the top, so we will divide it to the other side afterwards. So if you do that, that will give you the partial pressure of O2 equals 158 times 0.4 squared divided by 0.27 squared. Also, basically, everybody ends up in the opposite location, right, when they move across the equal sign. So he's on the bottom, he gets on top. He's on top, he gets on the bottom as he go across. At that point, if we do all that good stuff there, I erased it. Should not have done that. Let's try that again there. Now we'll go with a partial pressure of O2 of a whopping 347, it looks like maybe. And this one does need units, right? Because it is a pressure. We're not solving for K or anything like that. So remember, if you are solving for something like a pressure or a concentration, they do need units, right? So it's just K is the only thing that does not need units. There's often any questions on that calculation. Everything does sort of make sense, right? If we think about it with a value of Kp of 158, that is a large value of K, which means when this thing reaches equilibrium, I should mainly have products. And that would mean I have a lot of these guys. And I would say you probably have a lot if you got 347 atmospheres of pressure from the O2. And you definitely have a lot more of that flying around, right, than anything else, probably in this case. Any questions on that there? All right, seems like a good place to stop.